There are variations on permutation statistics that depend on posets P, and we're going to use them later in the course. So let's start looking at them now. Let's let P be a poset. And let's fix some permutation in Sn. We'll define the P descents of W to be the positions I where Wi is greater than Wi plus 1 in the poset P. And then ascents, P ascents of W will be positions I such that Wi is less than Wi plus 1 in the poset P. Similarly, we can define P exceedances of W to be this should be number of these, the number of indices I such that Wi is greater than I in the poset P. P anti-exceedances of W is the number of indices I such that Wi is less than I in the poset P. Then we can define major index by summing the descent set, the P descent set of the permutation. So the P major index of W is the sum over all I such that Wi is greater than Wi plus 1 in P, that index. And then inversions has a different definition that we might expect based on these. So here we're only counting greater than comparisons if the two elements are compared that way in the poset. So inversions is the number of pairs ij such that j is greater than I as integers. J appears before I. In W, and J is incomparable to I in P. So let's do an example with a 3-element poset. Let's write down all 6 permutations of 1, 2, 3. So we've got 3, 2, 1, 3, 1, 2, 2, 3, 1, 2, 1, 3, 1, 3, 2, 1, 2, 3. And then let's first do P descents of W. So mark them in there. 3 is greater than 2 as integers, but 3 is not greater than 2 in this poset, so that doesn't count. 2 is greater than 1 as integers, but 2 is not greater than 1 in this poset, so that doesn't count. So we have 0 P descents here. Your 3 is greater than 1, so that's 1 P descent. 3 is greater than 1, so that's 1 P descent. 2 is not greater than 1 in the poset. 3 is not greater than 2 in the post set. And then, of course, we have no descents there, even if we're thinking of integers. And the p ascents are, I guess, positions where we have 1 followed by 3, because those are the only two elements that are comparable in the post set. So looking for 1 followed by 3, there it is. There's 1 ascent, and then 0. Alright, so now we're looking for indices where the letter there is greater than that index in the post set P. So basically we're looking for 3's in position 1, because 3 and 1 are the only comparable elements in this post set. So here we've got a 3 in position 1, there we've got a 3 in position 1. And nowhere else do we have a letter in a position which is greater than that position in the post set. Alright, we're going to run out of space. Let me economize by putting anti-exceedances right here next to the exceedances. So here we want to see a 1 in position 3. So we want to see a letter in a position which is less than that position in the post set. So 1 in position 3. Here we've got 1. No. Yes. No. 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 And let's do inversions here. Well, actually, let's do major index first. So P major index of W, and then we can do P inversions of W. So we just sum the descents, the P descents. So there aren't any here. There's 1 there in position 1. There's 1 here in position 2. None, none, none. Alright, P inversions are greater numbers followed by lower numbers, and they have to be incomparable in the post set. So 3 followed by 2 counts because 3 is incomparable to 2. 3 followed by 1 does not count because 3 is greater than 1 in the post set. And then 2 followed by 1 counts because they're incomparable. So that's 2. So we're looking for basically 3, 2, and 2, 1. There's 3 before 2. There's 1. 3 before 2, no, but 2 before 1. So there's 1. 3 before 2, no, but 2 before 1. So that's 1. 3 before 2. And then we don't have any here. So we can see from this table that in this example, P descents, P ascents, P exceedances, and P anti-exceedances are all equally distributed because we see 2 1s and 4 0s in all 4 cases. We might guess that major index and inversions would be equally distributed just because that's how they are for SN if we're not using a post set analog, but that's not the case because here we see a 4 zeros, a 1 and a 2. Here we see 1 0, 4 1s, and a 2. Now it turns out that for any post set P, we have that P descents, P ascents, P exceedances, and P anti-exceedances are equally distributed. We put the similar sign in between them. These are all equally distributed. So the proof idea is that the proof is exactly the same as before. So that is P ascents of W equal P descents of W reverse. So sending a permutation to a reverse is a bijection on the symmetric group to itself that sends this statistic to that statistic. And then P anti-exceedances of W are equal to P exceedances of W inverse. So sending a permutation to its inverse sends this statistic to that statistic. And then P descents of sigma of W, where sigma is the parenthesis erasing bijection, are equal to anti-exceedances, P anti-exceedances of W. So remember, we have to write the permutation in standard cycle notation before we erase the parentheses. So this is proposition 3.5. In the paper Characters and Chromatic Symmetric Functions. Which is on your syllabus. Meaning there's a link on your syllabus to this paper, which is on my webpage. All right, so what about major index and inversions? We haven't said anything interesting about them. But there is something interesting to say, at least I think, in conjecture. Let's look at what happens if we add these together. A mathematician named Rawlings did this. I'm going to call this statistic the P Rawlings statistic. So this is P major index plus P inversions. So if we add these together, we get 2, 2, 3, 1, 1, 0. Now these numbers might look familiar because this is the same distribution as regular inversions or regular major index. If we put regular inversions here, we've got 3 inversions, 3, 1, and 3, 2 are 2 inversions, 2, 1, and 3, 1 are 2 inversions, 2, 1 is a single inversion, 3, 2 is a single inversion, there's no inversions here. So we've got a 0, 2 1s, 2 2s, and a 3. So I guess Rawlings, the P Rawlings statistic is distributed just like inversions, no P, just regular inversions. At least when P is that poset. So the question is, do we have for all P that Rawlings P statistic of W is distributed just like inversions. So I guess on Sn is the right way to write that. So are these two, is the p-Rawlings statistic a Mahonian statistic? Oops, there should be no p here. So is the p-Rawlings statistic a Mahonian statistic? Well, this isn't known to be true, which is why I've written question here. So far, I've tried p equal to this poset, and this poset 3 plus 1. And the equidistribution worked both times. So it works for both of these posets. Now Rawlings showed that the equidistribution works for posets pk defined by j is greater than I in pk if j is greater than or equal to I plus k as integers. So it definitely works for some posets. He actually wasn't working with posets, but his result can be stated in terms of posets, just like this. So again, I tried these. Now, an idea for proving this might be insert the letters from largest to smallest one at a time and watch the Rawlings statistic go up with each insertion. So we'll insert the letters one at a time. Largest to smallest. And we'll watch the p-Rawlings statistic increase with each insertion. That is, it's going to be 0 for one letter because there's no inversions or descents. And then hopefully with insertion of the next letter it would increase by 0 or 1. And then increase with the insertion of the third letter it would increase by 0, 1, or 2. With the insertion of the fourth letter it would increase by 0, 1, 2, or 3. Unfortunately, this proof doesn't work out. This proof idea doesn't work. So for example, Let's look at this poset. And let's look at, suppose we've inserted 2, 3, and 4. And now we want to insert 1 in all the possible different places. So we have 1, 2, 3, 4, 2, 1, 3, 4, 2, 3, 1, 4, 2, 3, 4, 1. Now for this poset, the equidistribution result is true. So it can't be that I picked a bad poset. So there's no inversions or no major index here. So maybe we can compute the statistic by looking at the major index and inversions separately. I want to look at major index inversions, Rawlings statistic, and then the change. So let me give myself more room here. Okay, so we'll look at how much the Rawlings statistic goes up each time. Major index is 0 here, 0 there. 2 is not greater than 1, so major index is still 0 there. 3 is greater than 1. That's a descent, so there's a major index of 2 because the descent is position 2. 2, 3, 4, 1. 4 is greater than 1, so that's a descent in position 3 and a major index of 3. No inversions here. No inversions there. 2, 1 counts as an inversion because 2 and 1 are incomparable. 2, 1 counts as an inversion. 3, 1 doesn't because 3 is greater than 1 in the poset. So 1 inversion. 2 counts as an inversion, but not 3, 1, not 4, 1. So the Rawlings statistic is 0, 1, 3, and 4. And, well, I guess I didn't need an extra column for the change in Rawlings statistic because if the original is 0, then Rawlings statistic is equal to the change. We went up by 0, went up by 1, went up by 3, went up by 4. I kind of wished we had gone up by 0, 1, 2, and 3. But we've got this weird jump of 4. And although it doesn't work out neatly right here, if we write down all 24 permutations and compute Rawlings statistic, we get 1, 3, 5, 6, 5, 3, 1, which are the coefficients of quantum 4 factorial. So for your homework, I'm assigning all of you a different poset, and I want you to do this experiment too. Write out the 24 permutations in S4, compute Rawlings statistic for your poset, and we'll see if you got the same answer I did. If you did, maybe we have a nice conjecture about a new Mahonian permutation statistic. Although we don't have a proof outline yet, because this proof, I'm afraid, is not going to work. The end.